Last session, we introduced what we mean by covariant shift, which is basically the statistics of each layer's inputs changing during training. Then we said we want to do batch normalization to mitigate that effect. And then batch normalization had two parts. One was training and one is testing. During training, things are allowed to be random. So it is random because you are taking mini batches of your data. And then we said we take a mini batch. We take the mean of that mini batch, subtract it from X. The input to that particular layer is X. We subtract the mean and divide by the standard deviation. And then that epsilon is just a parameter to avoid dividing by 0. But then if you do that, you run into trouble because everything that goes inside your activation function is going to have a mean 0 and unit variance. To counter that effect, you multiply by gamma, which is acting as your standard deviation. And then you're adding a bias, which is acting as your mean. And these are going to be learned during training. And every operation is element-wise. And one thing to note is that the gradients of your loss function flow through mu and sigma. So batch normalization is sort of anticipating what's going to happen as the parameters change. Then during testing, and in particular inference, you need to put a single number or a single vector for things to be deterministic, not to depend on your mini batch. That's why during training, you keep a running average of your mean and variance. And basically mu is that running average and sigma is that standard deviation. So we stopped here. Any questions up until this point? Now this is for a fully connected network. This is for a linear combination of the input to this particular layer. U is the input and W times U is X. And as you can see, this is a linear combination. You're just multiplying a vector by a matrix. What happens in the case of convolutional neural networks? For convolution, the input X is gonna be a tensor. It's gonna have P pixels in the X dimension, Q pixels in the Y dimension, and you're gonna have D channels or D filters. What you do is you take the number of the size of your mini batch, which is M, multiply it by P and Q. So all of these are gonna be your data now, and the effective size of your mini batch increases by P times Q. And then you do your mean and a standard deviation on that. Basically, batch norm is being done per feature map. So you're doing it per each dimension of your feature map. So is that clear? So not only you do your summation necessary for computing your mean and variance on your mini batch, on the number of images that just went into your neural network, but also pixel-wise. You're doing a summation over the pixels as well. And then that's gonna give you your mean and a standard deviation, which is gonna be in RD. So your mean and a standard deviation is not gonna be in R, P times Q times D, but rather it's gonna be in D. And then everything that you see here, this subtraction and division, are gonna be broadcasted. For those of you who know Python, you know that if you subtract a vector from a matrix, then the vector is going to turn into a matrix having the same size as your x, and then everything is going to get subtracted. So first your vectors are going to turn into matrices, and then you do your subtraction or division or multiplication. That's the concept of broadcasting. Is everything clear?
Seems okay.
Okay, perfect. So what are some of the benefits of batch normalization? You can get away with a higher learning rate because now things are more stable. Basically, you are taking care of the covariate shift, and these inputs to your activation are not going to have crazy values. Think about it. If G is a sigmoid, and then you don't do batch normalization, and this X gets too big, basically this input, then you're in the saturating regime of your activation function. And everything is going to turn into a constant, and then its derivative is going to be 0. So you can get away with higher learning rate. The method is now less sensitive to initialization because we are doing, in the end, an optimization. If you remember the first lecture, it was all about optimization methods. And optimization methods depend on the initial condition, basically the initial values of your weights and biases. And in the next topic, I will talk about how to properly initialize your neural networks. But for now, batch normalization is going to make things less sensitive to initialization. Because whatever your initialization is, you are subtracting the mean and the variance. So your data are going to be nice. Things are going to be less sensitive to activation function.
Wait, sorry. When you say initialization, do you mean initialization of weights or like initial training data?
No, initialization of weights and biases.
Okay.
In the end, you're going to write a loss function, and that loss function is a function of these weights and biases. And the role of training is to find the best combination of weights and biases.
Right.
But then your algorithm, let's say Adam, has to start with a good guess. If the initial guess for these parameters are very off, then there is no hope for training. Okay? So initialization is important. If you initialize everything with 0, there is no signal to propagate, and then you're going to get stuck at 0, for instance.
Right. And how does batch normalization sort of help you become less sensitive to that?
So the way it does it, it's by taking care of the covariate shifts. So whatever the weights and biases are, whatever this W is, you get an X, and from that X, you are subtracting the mean and the variance. So it's going to center it.
Oh, I see. Thank you.
So see, batch normalization is happening after the multiplication. So that's why it's less sensitive to initialization. It's going to be less sensitive to the choice of activation function, because now the input to your G function is going to be mostly centered around 0. So these numbers are not going to get too big or too small. And if you take a look at, for instance, the sigmoid activation function or tanh, it's going to stay in the regime where it's mostly linear. It's not going to go into the nonlinear parts and then saturate. Okay. It has some regularization effect. Why? Because things are random. Each time your neural network is sort of random because of different means and variances. So it has a similar effect to dropout because of the randomness you're introducing. and then it preserves gradient magnitudes. This is a maybe, so this needs further investigation. So basically, you need to be careful, write down your gradients and see what the magnitudes are. So these are the benefits of batch normalization. To see what I mean by covariate shift, first of all, what is the benefit? This is MNIST data set, and you are training a simple neural network on the MNIST digits data set. This is with batch. This is without batch normalization. This is with batch normalization. So you're converging much faster. And what the y-axis is basically the accuracy on the test data. So this is actually the generalization error, how your method generalizes. But then to see a concept of covariate shift, the input to a particular activation, G, is, for instance, in this case, it's going to be WU plus B. That input, you can take its mean and variance. So what we are plotting here is not actually the mean. You can take the median and then the upper quartile and lower quartile, and then you can just plot that. Basically, we are plotting the statistics of this during training. As you can see, it's nasty. It goes up and down, and it's not symmetric. But after batch normalization, the input to your activation is sort of behaving nicer and smoother. You're most of the time around 0, and then that's basically a way to plot your distribution. Okay. And these numbers are 15, half, and 85 percentiles that you are seeing here in this plot. So this is covariate shift. This is you removed covariate shift by this trick. So let's see it in action. This is the inception network, basically GoogleNet, the one that we covered last session. And this is the number of training steps. And the y-axis is the accuracy, and it's getting closer to, I don't know, 70% accurate. That's the inception module, and this is how many iterations you have to wait for your method to converge to this number. With batch normalization, this is the only change that you do for this red dashed line is introduce batch normalization, and you already cut the training, the amount of training necessary, I would say less than half compared to inception. Then you have batch normalization with 5 times bigger learning rate, which is going to get you here much faster. Then you have batch normalization 30 times faster. Basically, that's your learning rate 30 times bigger. You can change the sigmoid. This is because we just made a claim that batch normalization is less sensitive to activation functions. You change the activation function to sigmoid, and this is what you get. And these blue diamonds is just how many iterations it takes to reach the accuracy of the inception model. So it's really beneficial. At that time, this paper is a breakthrough when they wrote it in 2015. So if you think about it, these are really huge claims to be making when you're training a neural network.
Can I ask a quick question? Um, so beta and gamma are parameters learned on the scale of like an entire layer. Is that correct? As opposed to like a single neuron? Like for your in the normal situation, your bias is applied to each connection, right? But in this case, beta applies to every single connection in a dense layer, for example.
No, it is actually, it has the same size as B. Beta
Okay.
has the same size as B.
So
So
you're
it's just
learning,
replacing the bias.
okay. So you have a different one for each connection.
Per each layer, you have a different one. And
But you
per
don't,
dimension, you have a different scalar, if that's what you mean.
but in like a single dense layer, if you have like a bunch of neurons, each neuron would have their own bias, right?
Yes, each output neuron will have its own bias. Basically, each D is going to have its own bias.
Okay. Oh, and I see. Okay, that notation there. So each output neuron has their own beta in this case and their own gamma as well. Okay.
Yes, but these are vectorized.
Mm-hmm.
Notation here. This is a vector of the same size as B.
Yeah. Okay. Thank you.
Yeah. Any other questions? So yeah, beta is acting the role of B, because as you subtract the mean, B is gonna disappear.
Are there any cons, any like drawbacks to batch normalization in a network?
One drawback is that this is sort of random things that are happening during training. It depends on the batch. One drawback maybe is that you cannot get away with only one sample. If M is 1, then you're in trouble, because the standard deviation of a number is going to be 0, and then most of the time you're dividing by 0. So batch normalization with a batch size of 1 is going to fail.
How close does this end up being if you sort of append a layer onto the front of your network that does this and then train the mean over time?
You could do that, but then your mean is your parameter. And then what is the data to train that parameter is probably this mean that you're computing here. You could do that. You can say x minus a parameter divided by sigma squared, which one? This one is also a parameter. But then you need to train this separately. You cannot use the same loss that you have for gamma and beta and w to train mu and sigma. This has to be computed differently.
Okay.
So this is external to your data, to the loss function that you write.
It seems like a lot of these regularization techniques end up being external to the network.
Yes, exactly. So actually, this paper, batch normalization, they're using the inception model, the one from the previous slide. And they make improvements, actually huge improvements over that model. So what changes do they make? They remove dropout altogether. They say that we don't need it anymore, because batch normalization is sort of doing the regularization on its own. They increase their learning rate, which is this plot on the left, which means that they don't have to look at their computer training for 30 million iterations, but they can do it, I don't know, 14 million iterations. So it's a difference between 1 week versus 3 days, 4 days of staring at your computer and waiting for your results. Okay, that's a huge gain. They accelerate the learning rate decay. So usually when you're training your neural networks, as the training progresses, you usually see that the loss is dropping for some reason. at those points, they're reducing their learning rate. So when they say they accelerate the learning rate decay, they do it faster. Basically, they do these jumps faster for the training. There is a weight decay, which is equivalent to L2 weight regularization. And this was part of AlexNet. And most neural networks do that. There is this weight decay, and they want their weights to go towards zero. It's usually a very small parameter, and they actually reduce that even further. So apparently there is no need for, not much need for weight regularization. Do you remember that nasty local response normalization? So after this paper, actually most of neural networks for classification don't use that anymore. They don't use local response normalization. And they shuffle the training examples more thoroughly, because the more random things are to the eyes of the neural network, and the more independent are those samples, the network is going to learn faster.
How sensitive is this to batch size then?
So usually the way that you train your neural networks is that you choose your M as big as possible so that it fits the data and the network itself, fits on the GPU. But then how sensitive it is, that I don't have a definite answer to. That depends on the model that you're training. So that I don't know. And these are some of the results that you see. There is GoogleNet, the inception model. They had this resolution, if you remember, 224. And it was an ensemble model. So they were using 7 models doing the prediction and in the end aggregating their predictions. And they were using 144 crops per image for things to be translation invariant. And this was their top 5 error. And you can compare it to 4.9 when you do an ensemble of batch normalization neural networks. So it's a huge gain. So batch normalization is really powerful. That's the message. And it's really easy to implement. And it's already implemented in most of your neural network packages. You just say, I want a batch normalization layer and put it on top of my, I don't know, convolution.
So that number for models, is that independent, like ensemble models, right?
Yes, so usually the way that they do it is you train multiple models with different changes in your hyperparameters and weight initialization. A couple of these models, not all of them, are coming from different initializations for weights and biases.
Cool.
Then
Nice.
in the end, and some of them are a combination of being trained by a learning rate 5 times bigger, some of them with a sigmoid. So these types of changes. So minor changes, but in the end, it has a huge effect. Like from 5.82, you drop it to 4.9. Because remember, what is the aim here? There is this challenge that you have to win. So whatever changes that you make to your neural network, in the end, that's your objective, to reduce your top 5 error rate or top 1 error rate. And the competition is fierce. So it's not easy to improve by such a huge margin. Any other questions? Are those batch norm models including batch normalization once or multiple times in the network? No, this is for one layer. Usually after each convolution, there is a batch norm. So in your neural network, you have multiple layers, and each layer usually has a couple of convolutions. After each convolution, there is a batch norm. Does that answer your question? Any other questions before I change the topic?
Just to follow up on that real quick. So in practice, you will put like as many batch norm layers as there are convolution or dense layers in your network, essentially.
Yes, that's correct.
Okay, thanks.
Some of them might not have it. Probably the initial convolutions, the one closer to your input, because the input is already normalized.
Mm-hmm.
Usually your images, you take the image, subtract the mean, and then that's going to be your input to your neural network,
Mm-hmm.
your convolutional neural network. Okay.
And would that be inserted before or after max pooling, or does it not make a difference?
It makes a difference. And then we are going to go over the best place for batch norm in the future, in some future papers.
Okay.
But for now, after your convolution, you can put a batch norm. Any other questions? See, these are easy questions to ask and then easy to answer, but then you have to answer them on a computer. You might say, why not put batch norm right after U and then multiply it by weight? The people who wrote this paper actually did that, and it just doesn't work. Okay. Sometimes the answers are as simple as that. It doesn't work. The network doesn't converge. Any other questions? So the next topic is gonna be about initialization. We never talked about that. I was waiting until this moment. What is the proper way to initialize a neural network? What are the proper initial values for weights and biases? Can anybody answer that? Or what should we take into account when we want to answer that question?
You might want the map to be like a full rank map of some kind.
Not really. Any other thoughts? What might go wrong? Let's do it this way. Let's remove batch norm. Let's remove G. Then you have a bunch of matrices that are being multiplied by each other. And this multiplication is being done 16 times. Let's talk about VGG 16, where you have 16 layers. So you have 16 of these W's being multiplied by each other until you reach your image. What's wrong with multiplication?
Well, on a machine, it's not necessarily precise.
That's one thing. And mathematically, what can go wrong?
It can blow up.
Exactly. So whenever you see multiplication and you have a lot of them being multiplied together, a lot of W's, two things could happen. Either those weights have an eigenvalue of less than 1, then everything is going to collapse to 0 by the end of your output, or it's going to explode. Yeah, Jacob, you're right. It either grows or it shrinks very fast. So multiplication is dangerous. So we have to be careful with initializing these weights properly. There's another catch. Even for a single layer, you might end up in a regime where G saturates. What if you initialize your weights such that X is always negative? And then you are doing ReLU. That's your activation function.
You get a bunch of zeros and it'll propagate zeros forever and you won't get any information.
Exactly. So two things matter. One is this G. One is these guys being multiplied together a lot of times.